So today we're going to go over trajectories and how to calculate them. So the end goal is going to be this red tower where we have this blue trajectory. It only has a point and I have the angle I want it to shoot at, and it's going to calculate how fast the projectile should go and the time it will take to get there. Now before we get there, we're going to go over a handful of other examples. First of which is going to be an Angry Birds trajectory. It's just going to have the angle and the speed based on this little UI here, and then we will calculate the trajectory. Next, we're going to calculate the trajectory based on an angle and a point. So the point is going to be this red Godot icon, and we can move it to wherever we want, and it's going to calculate the speed and the time that it takes this projectile to get there. Then we're going to make this red tower where we have the enemy position, and we're going to want to shoot this projectile and make it look nice. And then we will also, as a bonus, go over this purple tower. This purple tower actually uses a tween and kind of fakes the same thing as all of these calculations. It just takes the position and tweens between the two spots. Then after we figure out how to make these, we'll do a comparison on performance between these two types of towers. Then at the end, we're going to go over some of the math that it took to make the formulas that I'm going to go over in the scripts. I'm not going to go over them in detail right away because I know a lot of you aren't really going to care that much about why they work, just as long as they work. So I'll explain the math at the very end. So first of all, we have this Angry Birds trajectory that we're going to work on. It's just a node 2D with a line 2D that we're going to be adding an array of points to in the script. We have a pivot, which is just going to be this point, and then this texture progress is kind of offset to pivot nicely with the pivot point. So this texture progress is going to go from 0 to 100, and the textures are just this little cone-shaped Godot icon, and both the under and the progress are the same icon. I just tinted the under icon to lose all of its color and be gray with less alpha. We're going to have a few different variables. The strength is just going to be the current strength of that texture progress, so the speed we're going to send the projectile on. We're going to have the aiming be on or off, depending on whether we're moving the mouse with the left button clicked or without the left button clicked. That way we can control when we move this UI or this strength. So gravity is going to be negative 9.8. I still have it as negative, even though the y coordinates in a computer grid are inverted compared to a normal math textbook. I like to change everything to be able to do my calculations as if they were in a math book in the real world. It just makes more sense to me, and then at the very end I'll invert it, that way it looks correct on the computer. So before we actually get to the calculation, how I'm turning the aiming on and off is with the action button, which is the left click on the mouse. When it is on, it'll be true. When it is off, it'll be false. And when we are aiming, I will measure how far the mouse has moved, and I will adjust the strength. So every time I adjust the strength, it's going to change this number. I had to put self strength, that way it would trigger the set get. So this set get function is going to change the strength number, and we're going to clamp it between 0 and 100, since that's what our minimum and our maximum value are. And this check is just to make sure that we don't get an error. Set gets run at the beginning of a scene or when they start up. Sometimes they can call this part of the script before the texture progress is actually in the scene tree. So then we'll set the texture progress value, that way you can see the UI changing. And then we will calculate the trajectory. Now the last thing we do before we actually calculate anything, in the physics process, if we're aiming, we're going to set the rotation, which is in radians, to the global position angle to point, which is a built-in function in Godot, and then we will get the global mouse position, and pi flips it around 180 degrees, since if you don't have that pi, it's going to point away from the mouse. So after we figure out the rotation, we can do the calculation. Now in the calculate trajectory, what we're going to want to get is an array of points that we're going to add to the line 2D. So we create an empty array, then this total airtime is just an arbitrary number that I've picked for this first example to make it easier, so we don't have to figure out how much time it's going to take. We just kind of set it to 10. In the next examples, we'll have to actually figure out how long the projectile should be in the air. So when we talk about an x component or a y component, that's going to be referring to the x and the y part of this triangle. This is a right triangle. So the speed is how fast the projectile is moving, and we're going to want to separate that speed into how fast it's going up and how fast it's going to the side. And you can figure that out if you have the speed and you have your angle. We're going to take that speed, or in this case the strength of that texture progress, that strength variable, and we're going to multiply it by the cosine of the angle of the pivot. So the cosine goes with the x component and the sine goes with the y component. Now I have this -1 here because if you look in the pivot, the rotation degrees, if you have it at 0, it points to the right. We're trying to measure how far it goes up from here, so counterclockwise. Now, when you add 45 to the rotation degrees, it adds those degrees clockwise, so it's the opposite of what we want. So in this case, we have to multiply that angle by -1. So after we find out how fast it's moving to the right and how fast it's moving up, we can do the calculations of where the points should be. So for point and number of points, and I just picked 50 because it made a nice little arc, we're going to have the time. So this is going to be the current time of this point that we're doing. We're going to have that be the total airtime times by the point. So what this number is just going to be either any number between 0 and 49 divided by the number of points. So in simpler terms, this part right here gives us a number between 0 and 1, and we're going to multiply that by the total airtime so we know how far we are through that total airtime. So if it's 0, we're at the beginning, or if it's 1, we will be at the end of that airtime. So the x is easy to figure out because there's no acceleration or gravity to deal with, so it's just going to be time times by the x component. So the y is a little bit more difficult to figure out because we have to deal with gravity. So the formal function that we have is right here. So this is just how far we've gone is equal to our initial speed times by time plus 1/2 acceleration times squared. So acceleration is going to be our gravity. Our initial speed is going to be our y component. Our time is time, and then we have time squared. Now I just did times times time since it's just a little bit cleaner than actually doing an exponent in Godot. And then this times by -1 is because I am flipping the y to actually work with the computer grid opposed to a normal math grid. So each time we're going to do this calculation, for every point in the number of points, we'll append that point to this array. And then we will add this array to the points in the line 2D. So what you end up with is this trajectory that you get. Now in our next example, we're going to have to figure out a few more things. We're not going to know the speed of our projectile or the time. We're going to have to figure that out based on how far away the target is from the starting point. So just a quick setup of the nodes. We're going to have the trajectory. This is just the container, and we just have two different sprites. I just had them to be different colors so we could tell the difference between them. The start is the blue, the end is the red, and we have, again, a line 2D that we will add all of our points to. So again, we have a number of points and the gravity, and we're going to calculate the trajectory every physics frame. And this line right here is just so I can move that sprite around to show in the example. So this next part is very specific to my game that I'm making right now. Most people won't need this if they're finding the trajectory. So I am making an isometric game, so I always want the arch to go up and then come back down, so it always looks like we're looking from an isometric point of view at this trajectory. Now, I'm finding the dot product to find whether this position is to the right or to the left and how far up and down it is. So the first thing we're going to do is take a vector 2 1, 0, so just a line to the right. We're going to get the dot product of end position minus the start position, and we're going to normalize that. So what this line does is find out whether it should be positive to the right or if it should be negative to the left. So when we have our circle, this is going to be 90 degrees. So we're going to add 45 degrees if we want it to be to the left, and we're going to minus 45 degrees if we want it to be to the right. So what's going to happen is if the dot product is 1, or the target is directly to the right of the starting point, it's going to minus those 45 degrees. If it's directly to the left, it's going to add those 45 degrees because the dot product will be -1. Now we're going to need the distance between the start and the end. So we're going to take the end and we're going to minus the starting position. And we just need the x for this, and we need the y for this, and we're going to flip it so that way it's like normal math. That way I can do my calculations, and then at the end I will flip it back. So this is not our x component and our y component. So what these are measuring is the total distance between the two. So the x distance is going to be measuring how far to the right or to the left the ending point is from the start, and the y dis is going to just be measuring this length right here. And after we have those lengths, and we have the angle, we can actually dump those numbers into this terribly ugly looking formula that I have right here. And at the end of the video, I'm going to go over exactly how I got this formula. But for right now, we're just going to accept the fact that if you type all of this in and feed it these three variables, it will return the speed, or the hypotenuse, and then we will be able to use that speed to find our y component and our x component. Now this angle that we have up here, this is in degrees, not in radians, so cosine in Godot needs to have a radian. So we use this degree to radian each time. We have the cosine of that angle multiplied by our speed, and we get our x component and our y component. Our total time is going to take the total distance, that x distance between the two nodes. We're going to divide it by our x component. Then again, we'll take for point in number of points. We're going to figure out at what time step we are at, again with the total time times the point divided by number of points. And exactly as we did before, we're going to find where the x value of that point should be. We're going to find where that y value of the point should be, and then we're going to append that vector. We're going to have to add that to the start position's global position, and then we will add that array of points to our line 2D. And that creates an arc that connects the two. So how do we use that information to make a tower that's actually going to use that calculation? We're not actually going to change anything about the tower. We're just going to be changing the projectile. So instead of creating a line 2D, we're actually going to make a path. So this path, just like our line 2D, does not actually have the curve that we need. We're going to create that curve when it is created, and then we will set the path follow along that path, which is going to be just a simple sprite, and we're going to use that tween to actually move it along. In my previous videos, I've made other projectiles. So when the projectile is made, the start function is immediately called, and it passes along the position that it should start from, and then also the target. Now the target is not a point, it is an object in the game, so we're going to have to figure out the target's global position. So we'll set the starting position of this projectile to the position that it's been given, and then we're going to calculate the trajectory from our starting position to the global position of that target. So when we calculate this trajectory, it's going to be almost exactly the same as our previous example, except instead of having the end global position, we have these positions given to us, and they're going to be called underscore start and underscore end. So what we're going to do is, again, we'll need the array to hold all the points. We'll find the dot product in the same way to find whether it's to the right or to the left, and we will create our angle that will create that isometric feel. We will find the distances that we need, put those distances into this long equation to figure out the speed that we need, and from there we'll find our x component and our y component, our total time. We're going to create a new curve and add these points to the curve. I actually don't need to add it to this array. I actually don't even need this array in this exam because I'm going to just be adding the points directly to the curve. I am creating this new curve and we're going to add point. Add point is a built-in function with curve 2Ds. And so we'll add that point, and then we're going to set the curve. If you remember, this extends a path. So this variable is a built-in variable. We will set that new curve to it. And then to actually make the path follow move along that curve, we're going to interpolate that property with a tween, which just means we're going to make the unit offset, not just the offset. If you remember the difference between offset, this is the total distance along the path. We don't want to bother figuring out the distance. The unit offset is just from 0 to 1, and it doesn't matter how long it actually is. So 0 is the beginning, 1 is the end. We're going to interpolate that unit offset from 0 to 1 in a time that's going to be the total time divided by 10. This could definitely be a variable to change later, but I just thought 10 looked okay right now. And you can play around with the different types of tweens that you can use. I just used a trans quad because I thought it looked okay, but there's many different options, and I eased it in. Now, depending on what type of projectile you want, you might want to use ease in or you ease out. Basically, ease in makes it a little bit slower when it shoots, and ease out will make it slow down a little bit before it lands. It just depends on what effect you're going for in your game. And don't forget to start your tween, otherwise it will not do anything. And the last thing I should mention is in the tween node, there is a signal called tween completed. When a tween is completed, if the key is unit offset, so you need this colon here and unit offset, that way it knows what it was tweening. If it was the unit offset that the tween completed, we're going to cue free or make the bullet disappear. Now this is usually where you would do the effect of that bullet or that projectile blowing up, but we're going to do that in a different video. Right now we're just going to focus on the trajectory. So in the end, this is what we have. So now I know I used a tween to make the projectile move, but you can actually use the tween to cheat a little bit and not bother with these super long equations. So this is an additional projectile, so similar to what we just got done looking at, but another version of it. So this is actually an area 2D, and it's going to have a sprite. I actually added a shadow at the bottom to kind of give it a little bit of depth. It has a collision shape that we're not really going to use right now. So the tween is going to move this entire node or object directly at the target, and the animation player is actually going to be the one that makes the projectile move up and kind of do a fake trajectory. And the animation player will change the shadow a little bit. It's going to get a little bit bigger and lighter as the ball moves up, and when it comes back down, it'll get darker. So just a quick look at this trajectory animation. I just have one animation here, and the sprite, I have the position starting at the bottom, going up, peaking there, and going back down. Now, the main thing is that you have 0 and 0, and you have any number here, because we're actually going to set this number in the script using code. Now, the rotation, I don't think you actually notice with this one, but I'm rotating it a little bit, and I actually don't even bother changing the scale of this sprite right now. If you weren't doing isometric, you might want to make it bigger. You could make the scale, make it kind of pop a little bit bigger as it gets closer to you, but I don't think that would look good in my game currently. Now the shadow, this other sprite, I am moving the scale, I'm making it a little bit bigger, and the modulate, I'm just bringing the alpha down a little bit, that way the shadow is not quite so dark. Also, something I almost forgot about this animation player is the position of the sprite, so the going up and the coming back down. I played around with the easing quite a bit, so this is the first key, I eased it up, and the second key I eased it down quite a bit. Typically the easing would just be straight along, 1, Now this is only 1 second long, but we are going to actually change the length or the speed that it is played in the code. So let's go ahead and take a look at that. Now ironically, there's a lot of code here just to make the animation player work. Usually you use animation players to kind of avoid code, but this one required quite a bit of tweaking. So we're actually going to preload. So I saved that trajectory animation as a resource because that's going to become in very handy in just a minute. So I don't ever want that height of the projectile going up and coming back down to ever be more than 150, and the max time that the projectile is going to take to get to the enemy is going to be 2 seconds. And again, with the projectiles that in my game, we have this start function. And if you look at my previous videos, this is an inherited scene. So I have a start function in here that sets the rotation and the scale. I decided I wanted to keep those. And how you do that in Godot is you put dot start. So in an inherited scene, since I had a start function here, if I write a start function again, it will overwrite everything, but if you put dot start, it will run all of that code from the previous script. And if that doesn't make sense, you should check out the other videos explaining the projectiles, because I explained that in more depth there. So the time is actually going to be the position, and we're going to get the distance in a straight line to that global position. I have to have this target offset. That's only because I'm kind of silly and I have little aliens that are up in the air. So their actual position of the entire object is down on this path, and the position that I want it to aim at is hovering above that since they're little aliens. But we're going to get that distance and divide it by our max speed, which again is not a variable right here, but we have a max speed in our inherited or our parent script. So it's going to be 250 is the speed we have. And then we're going to interpolate the property just like before when we were following the path, but this is actually going to just go directly at the target. We're going to interpolate the property. The first thing you need is the object, so it's ourself. We're going to interpolate our own position from the starting position to that target position with the offset, so that way it aims at the actual alien. We're going to take that, it's going to take this amount of time. So we're going to do translinear, and I did ease out. So along with the tween, we're going to have the animation player that's actually making this fake trajectory that we have. These few lines here have to do with the fact that we have multiple animations going. So the reason why I had to preload this animation is we're going to actually set the height of the animation down here based on how far we need to shoot and how much time we have. And if we continually change this, so I'll just show you, take all that out, and if I run, so if you see how they're bouncing around kind of jaggedy, it's because they're all the same resource, and we're setting the different heights each time a different tower shoots, which will reset all of the heights of every single projectile out there. So it really looks jankety, it's really weird. So how we make a unique resource would be these 3 lines here. So we're going to duplicate that resource. That way, if we change anything on it, it doesn't change the original one. We're going to actually remove that trajectory and add a new one. And you have to remove it since I already have one in there, which wouldn't have been necessary, except it makes it easier for me to show that previous example of it being bad. We're going to find the position track. So we're going to look inside that animation. So we're going to get that animation. We're going to find track and sprite position. And how you get this string right here, we have sprite, which is the purple thing. I never actually renamed it to the projectile sprite. But if you look here and you hover here, that is how you find what you need to type in there. Sprite position. After we have kind of the path to finding our track that we need, we're going to get that animation again, and we're going to set that key value. First, we'll need the path to the track. Then this is which key it is. So if you remember, again, going back to the animation, this would be 0, this is number 1, this is 2, we want number 1. So we'll set number 1 to a vector 0, and we're just changing the height. We don't need to actually change left or right, so we're just leaving x as 0, and the height is going to be time divided by max time multiplied by the max height. Then we're going to change our playback speed to be 1 divided by the time, and we will play that animation. Now this is to make it so that the longer shots will take longer and the shorter shots will go quicker. Otherwise, your short little shots will take the same amount of time as one that goes about 5 or 6. And then when that tween again is completed, we'll have a signal that will cue free. I'm not even checking to see if it is the right key or not. I only have that one tween. So what you end up with is this. And since we programmed this last time, still click this button to shoot all of those projectiles out. I've tested this and I brought the number of shots per second to about 100. And my computer's really hot and not running very well right now because of my recording programs and just also making this video with everything going on. So my computer's really warm right now, but on previous tests, I've been able to get about 20 of these red towers, so the ones that are calculated and then it makes the path. I was able to get about 15 to 20 of these towers shooting at 100 shots per second. And the purple ones, I was only able to get about 6 or 7 before it started to slow things down. Now the last part of this video is going to be explaining how I got that really ugly equation that's down here. So we have this equation of movement here where it is basically how far the projectile has gone is equal to the initial speed times time, and then you add 1/2 acceleration times squared. So gravity in our case on the y, and this will all be 0 for the x. If you remember, we didn't have the speed and we also didn't have the time. So we have two variables that we need to figure out. Now we're going to split this equation into the x and the y components. We're going to solve the x equation for time and then stick that time variable into the y equation. That way we can figure out what the speed is. So again, what we're going to start by doing is in the x direction we don't have any acceleration, so this part of the equation's gone. We have the speed times the cosine of theta times time, and we want to solve for t. So we move t over to the other side. Now we have our y distance, and again we have the speed sine of theta t plus 1/2 gravity times time squared. So we're going to take this t and put it into this function. So we have, instead of this little t here, we have all of this garbly goop here. There should be a theta here. After we put that in there, we're going to solve for speed. So we're going to do things like, first off, there's a speed, and we're dividing by speed, so we can just cancel that out. And I'm doing a lot in just a few steps here, but I didn't feel like writing it completely out. So we're going to take this squared, we'll put it down here. We're going to move this to the other side of the equation. That way we can multiply everything by speed. So we'll multiply everything by speed and then take the square root of it, and what you end up with is this equation here. And if you have any questions about it, please let me know. But I know I went through this pretty quickly, so if you actually cared enough to watch to this part of the video and you still have questions, please let me know, because I know I explained this a little bit, but I still went through it pretty quickly. And there's a lot going on with both the math and in the game right now. So if any of it doesn't make any sense, please let me know in the comments. And if you have any suggestions for other things you would like to see in this game, please let me know.